254. Opening problem. Can you read the opening problem first? Do you have that? Who don't have a textbook? Who don't have textbook? Okay, no response. I assume everyone got, huh? Okay, you got your textbook. Okay, so now. Okay. So this is talking about, okay, Red is a pumpkin farmer. The pumpkin Red produced have an average of, this is the old one, okay, the old. Before the new farming technique. So the weight of the pumpkin, W is the weight of the pumpkin. Usually natural occurring things, it will be normally distributed. Okay, with a mean of 5 kg and a standard deviation of 0.5 kg. Okay. But in this case, they didn't say, okay, I assume it is normally distributed. Okay, so now he used a new farming. So he made this claim. Okay, with the technique, new technique, correct, it increased the weight of the pumpkins. That the average weight of the pumpkin is 5.2 kg. Okay, so now in this claim, I have to recognize the parameter. Okay, the parameter is the mean weight of the pumpkin. Okay, parameter means the statistical value that you try to prove. Okay, what is the population in here? What is the population in this case?
Number of pumpkins.
So all the pumpkin produced by all the pumpkin producers by Rick using the new farming technique. All right. So every time when you look at the claim, you have to know what is your parameter. Parameter, that means what are you trying to prove? You are trying to prove the, you are trying to prove this one. Oh, sorry. You are trying to prove the average weight of the pumpkin. So this is what you're trying to prove. So every time when you make a claim, you have to know what is the parameter in the claim and what is the population in the claim. Clear? Okay, I list out it. So in this question, they didn't tell you. So that is very important because when you do your folio, when you make your claim, then you have to tell me what is a parameter, what is a population. Okay, now you know how to make the parameter and the population? Hello?
I think.
Anyone? Everything you must make sure you know. Okay, so now, then they say, Rick friend argued that this, okay, so now Rick tried to take, okay, he get a sample. Oh, no. Okay. Actually, I add on to this. This is a claim. Okay, so he take the sample. He take a sample. So what is a sample? So now he take a sample and he got the weight as 5.2. So he said it's more than 5. Can or not? Can I base on the sample and talk about, okay, what do you mean by sample? Okay, before we go on, so what do you mean by sampling?
Taking a random pumpkin out of the population.
Yeah. What do you mean by sampling? Sampling means you take part of the population. So what is, so if you look at part A, sampling distribution, correct? That one I will explain later. So why do we, so now my question is, why do we take sample? My question is, why do we take sample? Why do we take sample? In this case, what do we want to know?
To get an estimation of population.
We want to know, okay, we want to know the true parameter of the population. So we want to know, in this case, we have to be very specific. We want to know what? The average, or we want to know the mean weight of pumpkin. So we have to be very specific. Pumpkin of produced by Rick using the new farming technique. So you see, in this case, I have specified the parameter. Here is the parameter and also the population. So why do we take samples? We take sample because we want to know the true parameter of a population. So now if I get a sample, okay, for example, I take, maybe for example, I say, okay, I take a sample. So when you take a sample, of, okay, when you take a sample, you have to know the sample size. A sample of size 20. So sample size I is using the symbol n. So it's 20. So out of this 20, I find the weight, then I find the mean. All right. So this symbol, so x is a weight. So x is called the sample mean. What is the sample size? 20 I put here. By 20. So maybe the total I get is, okay, let me just simply give you. Okay. Okay, 110, okay, kg. So I divide by 20, what do I get? Okay, I get 5.5. So this is the mean of a sample. So now the sample statistic. So this is called sample statistic. So this one we call it sample statistic. Our statistic is what? The mean. So this one we call it sample statistic. Okay, can this sample statistic represent the population statistic? My question is, can I say the mean weight of the pumpkin produce? Cannot. Why? Because sample is just part of the population. No, it's just a sample, and sample can vary. So this is my first sample. So when I get another sample, I will get another thing. Correct? Hello?
Yes, Miss.
Mm.
Miss, where do you get
Yes.
the 20?
Oh, no, I just simply put.
Okay.
I just simply go and pick the sample size. So now it's just one sample, and samples vary. So if you look at here, if I get the first sample number 1, okay, my sample size, I fix it at 20. Okay, first sample number 1, the sample mean is 110 divided by 20. So I get 5.5. When I get another sample, definitely it won't be the same, am I right? Maybe the total become 105 or 106. So I get another value. So you see, my sample can vary. So now, how do we find the true population parameter? How do we find the true population parameter? It's sample. Sample 3 will give me different things. Sample 4 will give me different thing. So what should we do? So what we need to do is, now we have to ask ourselves this question. What is sampling? Okay, who can tell me what is sampling? If in English, sampling means what? This is a continuous tenses or present tense. Is a continuous tense, correct? So that means it is telling you when you talk about sampling, you are looking at sample after sample after sample after sample. So what is sampling? Sampling means looking at sample after sample after sample many more of, very important, must be of the same size and from the same population. So that is called sampling. So now in this case, when we get the sample, what are we supposed to count? We are supposed to count the mean weight. So now the variable is the sample mean. Sample mean is our variable. So each sample that we get, we got infinite number of samples. You can imagine how many pumpkins are produced in that farm. A lot, correct? It can be thousands. So you can imagine out of the 1,000, you choose a sample of 20. Do you know how many samples can you have? Can someone use your calculator and tell me number of possible samples that you can take? Huh? Sure, 1,000. You know where to find your C?
3.4 times 10 to the power of 41.
3.4
4
times 10 to the power of 21.
41.
41.
I think,
So
yeah.
is it possible for us to take all the samples? Definitely not possible. So what we can do is, so our goal now, we want to know the distribution of this. We want to know what is our goal. We want to know the distribution of sample mean. So when I say distribution, you still remember when we talk about distribution, it can be skewed left, skewed right, and so on, correct? So now, so this is my variable. So now I try to get a plot graph, for example, okay? So now, everyone, I try to find a mean, and I round up to two significant, one decimal place. So I get. So I plot the graph. Maybe one sample is 5.5. I got sample, many of them. So I make the plot graph. So I may have some here, 5.6 and 5.4, then 5.6 here, and so on and so forth. So I will realize that if you get many, you will look at the shape. Okay, for anything, the shape will be some sort like a normal distribution. Is symmetrical. Very few which is very low, and very few which is very high. What is it? Is it the individual weight of the pumpkin I'm talking about?
No. Eh,
No, I'm talking about the mean weight of 20 pumpkins, a sample of 20. So this is my variable, right? So every sample, their sample means will vary. That's why we have a distribution. Okay? So after we know the distribution of this sampling, then what can we do? So that's why part A is called sampling distribution. Okay, and if you turn to your book, okay, so statisticians have found out that a very powerful theorem that tell us about the sampling distribution. That powerful theorem is called central limit theorem. Okay, so I'm going to explain now. So now, from in this chapter, the variable that we are going to talk about is sample mean distribution, and the other part is called sample proportion distribution. It's not the individual value. Are you clear? Okay. So I'm going to use this example and bring you to central limit theorem. Then I will come back to A again. So in this chapter, what are we going to study? We are going to talk about, you have to know what is sampling. So what is sampling?
sampling.
What is sampling? Hello?
Looking at the sample after sample after sample of the same size of the same population.
Yes. So that is the meaning of sampling. Are you clear? So now our goal is to what? We want to look at the sampling distribution. How is it look like? So that later it can help us to estimate the population parameter that we want to talk about. Are you clear? Hello? The sampling statistic, that means the sampling, in this case, I'm talking about the sampling mean, can change, can vary. So this is known as sampling variability. So now I'm going to talk about central limit theorem. Can I move? So first, if I ask you the question, what is sampling? You must be able to answer me. If you give a claim, you must know what is your parameter and from which population are you talking about. So every question from now onward, if you see the problem solving type, first of all, you have to know what is the parameter you want to talk about and what is the population from it. You want to draw the conclusion on this parameter. Got it? Okay, so now I'm going to talk about CLT. What is CLT? Turn to page 263, central limit theorem, okay? So now. So I'm going to talk about mean first. So for example, my initial, this is my population. Okay, this is my population. Okay, I'm talking about X is the weight of the pumpkin. We take this situation, Okay. So we assume this is X is normally distributed. Assume only, it may not. Or you prefer to not. Okay, maybe we take one that is not better so that you won't get confused with the other one. Okay. Okay. So the weight of the pumpkin produced by this farm has this type of distribution. Yeah, so this distribution, what do we call it? Hello,
Sampling distribution.
what type of distribution is it? Skewed left,
Left.
skewed right?
Negatively skewed to the left, yeah. Right.
You-
What was I saying?
Left
Left.
or negatively skewed. Okay, negatively skewed. So from this population, I'm going to draw samples. Many. I'm going to draw samples of size 20. So this is my sample distribution, not sampling distribution. So each of the sample, 20, I may have something like that. So I use point, okay? 20 point. Okay, this one. Yeah, this is the sample number 1. Then I have sample number 2. Okay, which may be like that. Okay, sample number 3. Many of them. Okay, so from each of these sample, I count the sample mean. So how do we write sample mean? What is the symbol?
X is the line on top.
Yeah, X with the bar on top. So each of the sample mean. So now I talk about my sample mean distribution. Sample mean distribution. That means my variable now is X bar 20. So according to CLT, if your sample size is more than 30, or what is our textbook say? Can you check our textbook? Can you go to page 263? Yeah, 264. If you look at the 264, it says many texts suggest that a rule of thumb, if n is greater than 30, to indicate n is large enough. So n is greater than 30 means n is large enough. Yeah, so we go by this thumb
What
of
does
it.
that mean?
That means your sample size must be more than 30. So that means our sample size here 20 may not be large enough. You can imagine how many pumpkins you produce in that. So 20 of them, how well can it represent?
So 30 is the general.
Yeah, it's a
minimum.
thumb of rule. Yeah, you can see this in page. Yeah, a minimum thumbs of rule. Depend on how big your population is. How big your population is. If, for example, my population is only made of 50 people, made of 50 only, do I need to do sampling? My question is, if my population is only 50, do I need to do sampling?
No.
No.
I can get all the data about the 50 of them easily. So why should I do sampling? So when do you use sampling? When do you do sampling? There is another question you can ask. There's another question you can ask yourself when you write in your folio. You say, why do we need to do sampling? If my population only consists of 100 people, can I collect the 100 data easily?
No.
Hello? You can. 100 of them, what, so what? Each one you take 5 minutes, 100 only take how long? But if I want to talk about cover all the Malaysian, all the pumpkin in this produced by this, definitely is impossible. Am I right? There are a lot. So that's why we need to do sampling. There is another reason. If the population size is big, so what you want to know, you want to estimate certain thing about the population, then you have to do sampling. So that's why the terms of rule is large enough. Okay, so sample mean distribution, okay, is large enough. The central limit theorem say that the sampling distribution. So this is my variable. Okay, since they say 30, we put it 30. Make our life, okay, 30. Yeah? So it will be normally distributed. The sample distribution is not normally distributed. The population also is not normally distributed. If the sample size is large enough, it will be normally distributed. So this is central limit theorem is a very powerful theorem. Okay, you ask me how statisticians know, they have to do the study. You can use your computer to do the simulation, but we have no time for this type of simulation. You can go and try. You type in 1,000 number, then you select, you ask the computer to select for you 30 of them, then find the mean. They can do that. Okay, there is a program to do, but you don't have to do that. So, hello? So that is the first thing. That is the first thing about central limit theorem. You go to page. Can you please go to page? You don't have to get into detail of this because you just apply this theorem. Can you go to page 264 of your textbook? Okay. So they say if the sample size is large enough, the sample mean distribution will be normally distributed. So normally distributed. Okay. Second thing, so this is the first thing of central limit theorem. Whether the population is normally distributed or not, it doesn't matter. The sample mean distribution will be normally distributed. Okay. Second thing, you also say that the mean of the sample mean distribution. So this is the mean of the sample mean distribution. This is how you write. How I read. The mean of the sample mean distribution is equal, is equal to the population mean. So how do I write population mean? Is my variable x. So this population mean, I have a value. Hello? Can or not?
Yes.
Okay. Third. So look, the mean of each sample should be quite close to the population mean, correct? They can't vary much, correct? Their variation should be smaller, correct, than the individual weight of the pumpkin, am I right? So the standard deviation of the sample mean. So how do I write this? Standard deviation of who? The variable is the sample mean. Is equal to the standard deviation of the population divided by square root of n. So the spread will be smaller for the sample mean. Are you okay? So this is CLT all about. This is the very powerful theorem to let us know the nature of the sampling distribution. So in real life, it's impossible for us to get all the possible samples. So that's why they imagine, that's why this come out, they come out this theorem. So a theorem is for us to use, for us to follow. So they have come with many, they have come to a conclusion that it works like that. So in real life, I told you already just now, you see or not? Is it possible for us to get all the possible samples? Is it possible? You work until next year also, you can't finish. Am I right? Do you know how big is this number? So it's impossible. So if we would take, so you imagine you take all the possible samples, and each sample you count the mean and you plot the graph of sample mean distribution. You will get like that. So when we talk about central limit theorem, what are we talking about? Are we talking about the individual weight of the pumpkin? Hello?
Yes.
Are we talking about the individual weight of the pumpkin? Is this the individual weight of the pumpkin? No. We are talking about a group of pumpkin, a samples of pumpkin. How many of them? 30 of them. I find their mean. I'm not talking about the individual weight of a pumpkin. I'm talking about the mean weight of a samples of 30 pumpkin. Are you okay? So that is called sampling distribution. You are not talking about the individual data. You are talking about the sample. Can or not? Okay, so very important thing, the claim. What is the parameter that you are talking about? From which population you want to draw that conclusion. So what is sampling? Sampling means you take sample after samples after samples after samples until infinite sample from the same size and from the same population, and you calculate the parameter that you want to talk about. Your parameter can be the mean, Your parameter can be the sum. Your parameter can be the proportion. Hello? Got it? And central limit theorem is a very powerful theorem to let us know how the distribution of sample mean or sample proportion or whatever you are talking about. Thumbs of rule, if you talk about sample mean, you make sure that the number of data you get for each sample must be more than 30. That is called the sample size. Okay, so if the sample size is large enough, then the distribution will be normally distributed with the mean equal to the population mean and the standard deviation equal to the population standard deviation divided by square root of n. So now I ask you, if I increase the n, what will happen to the standard deviation?
It will lower. It will become smaller.
Yeah. So that means if your sample size is larger, then the deviation will be smaller, correct? Because the sample is a better representation. The mean of the sample will be a better representation of the population mean. So the standard deviation of the sample mean distribution will drop if you follow this formula. The variation of the sample mean will be less. Got it? Okay, Anna? Yeah, so I explained what you mean by parameter. I explained how to state the population. I've explained to you what do you mean by sampling. Then the powerful theorem that help us to know the shape of the sampling distribution. Can Anna?
Yeah.
Yeah, okay. So now I want to go to part A. So it's a lot of explanation. Actually, if you really want to get into central limit theorem, it's very long, but we have no time to get into detail. Okay, so now can you go to page 254, part A? Okay, let's go to example 1. Okay, so now I'm going to explain to you. This is not easy to understand. So example 1, I'm going to explain. Example 1. Okay, my population is only consists of 2 numbers. There is 2 and 3. So there is 2/3 and 1/3. So this is my population. Find the probability distribution of S2. Okay, I want to explain to you what is my S2. S2 means sum of samples of size 2. So the sample size is 2. The S represent the sum. So now that means in the box, listen, I got 2 and 3. So when we talk about sample, it must be a random sample. Random sample means every one in the population has an equal chance to be selected. So that means you draw one. Like for example, I draw out two. I must put back two again, then do the second draw. That means it's with indirectly must be with replacement. Are you clear? That is called equal chance to be selected. So that means when you talk about the sum, I can have this. These are the outcome. I can have 2, 2, 2, 3, 2, 3, 2, or 3, 3. Am I right? So this one, the sum is 4. This one, the sum is 5. This one, the sum is 5. This one, the sum is 6. So that's why my S2 variable will be 4, 5, and 6. Now you understand? Hello? Do you get me? From the population of only 2 number, you draw 2 number.
Oh, makes sense. Okay.
Understand? So that is a, can I from a population of 2 number, I draw 3 number? Can. That is what is in the part, the other part. So what is the probability of getting both 2? Sum of, so the probability you learned before. 2/3 times 2/3, correct? So this is 4/9. To get a 5, you have both. So it's 2 times of 2/3 times 1/3. So the probability will be 4/9 also. And to get 3, 3 is 1/9. Are you okay? So from
Yes.
here, you can find the mean and the standard deviation using your 1-var stack. Okay. Hello? Then, so you from 2 number, I also can have the sum of 3 numbers. It's possible. Are you okay? Okay. So according to this investigation, okay, if my population X has the mean or mu, this is my population. So this is a formula that you have to remember. And the standard deviation of sigma, this is all for population. So SN distribution. What is my SN distribution? Sum of the n of sample size n. Okay, it will be the mean of SN will be n, the mean of the population.
Wait,
Okay.
what's SN distribution again? Oh, wait, the mean. Okay.
Can or not? The N here tell you the sample size. The S tell you is the sum. Okay, and the standard deviation of the SN distribution will be equal to square root of N times by the standard deviation of the population. So this is the relationship. So this formula you have to remember. Are you okay?
Yep.
Okay, so tentatively you do part A first, then after that I will talk about the distribution of the sample mean to you later. Okay, next tomorrow.
Okay.
Hello?
Yep.
Can I not?
Yes.
Okay. Okay, thank you, class.
All right. Thank you, Miss.
Thank you, Mr.
Thank you, Miss.
Yeah. Okay, I have to end the class. I got another class to go.